Okay, so why do we need to talk about this? Why is it important to draw these things other than just a silly exercise? A lot of compounds can only be drawn in this form. So one that they talk about in your book, and a lot of natural products do this also. So I'm going to switch to my other camera here so I can show you this. Maybe it works. Yeah.
So those two, like, to me are really the same.
Yeah.
I don't see them as different. Like,
Right.
You just look at the first one
Right.
from behind it, and that's the same.
That's right. So just looking at it like that, they're the same. They're just mirror images, but they're the same molecule. Yeah. What's going to change is when we start putting stuff on there. When we start attaching things to it, that's when it'll change. But you're right, it's the same. So here's a puffer fish. And if you eat the puffer fish, you're at risk of being exposed to this toxin, tetrodotoxin, one of the most potent toxins known. And it seems complicated, but you'll notice that the molecule it is a complicated molecule, but you can see two of these chair conformations side by side here with these other molecules attached. And in a three-dimensional molecule like this, there's really no other way to draw this. Because of the way that it's all branched off, you can't draw it flat. You have to draw it in this form. Same thing goes for any type of sugar or carbohydrate chemistry. Carbohydrates make these types of conformations as well. And so when you look at starch structures, when you look at even things like sugar backbones in DNA, a lot of pharmaceutical compounds that have those types of components, it's important to be able to see how these types of things are formed. In fact, all of the sugars that have the same number of carbons, like glucose and galactose, and I don't know the whole list anymore, but you can look it up, xylose, I think that has fewer carbons. We'll get to that at the end of the semester, but all those only differ by whether they have these OH groups either in axial or equatorial up or down position. So in order to actually differentiate those from each other, you have to be able to draw these things and see them differently. And if you've drawn them at the wrong angle, you've actually drawn a totally different sugar, a totally different molecule. So if you're trying to communicate the chemistry of this guy, or just some sort of a pharmaceutical, you might see that. And especially, let's see, where else do we see things like that? Things like opioids, like codeine and morphine, those types of structures have those as well. Next time you have some sort of a medicine and you can take the prescription comes with a little paper with all the information about it, and that'll usually show a chemical structure. And you can see it, a lot of them will have these types of structures in them because it is a really common thing that exists because it's so stable. So it's a big part of our bodies, and it's a big part of then stuff that we would put into our bodies to interact with our bodies. Yeah. Mm-hmm.
There's two of these connected. When you're drawing them, does it matter which way you're drawing them?
It does, because if you drew it with them kind of in different flipped ways, it might be different. So we're going to look at that in just the small molecules here and how we can make sure to get the right ones. So let's first look at what happens when we just put one thing on this cyclohexane chair. So we're going to draw one of them. We'll draw this one first. The two different chairs? Not really, because they're the same, really. They're unless you put stuff on them, they're the same. So we just talk about them as the two chair conformations. There are two different possible ones for every molecule. So we'll start with a basic chair like this. And we're going to put one substituent on the very right-hand side on the axial bond. So we're going to draw an axial bond with, let's say, a methyl group on it. I'm going to express that on my model here with a big blue thing, just so we can all see it. It sticks out, but I'm basically looking at that. So now we want to draw what happens when this flips. So watch my model. You see do I have that the right way? No, I don't. There's the methyl group straight up, just like I've got it drawn up there. See that? If you want to follow along, you can try with yours too. Even though we haven't drawn the rest of the hydrogens in on ours here, we just drew that one. And in fact, just to be complete here, let's draw the hydrogen that's on that same carbon. So that's going to be on the equatorial down bond going off and to the right. Maybe that hydrogen right there. All right. So now, watch what happens when we flip this. We flip this side up, and we flip this side down, and we now have the other chair. So what happened to that methyl group? It's still pointing up, but now instead of straight up axial, it's equatorial up, kind of out and up. And then the hydrogen is still down, but now it's straight down, axial down, instead of the equatorial down where it was. So we're going to draw that flip now. This is an equilibrium type process, so we draw two little arrows showing that it can go back and forth chemically. And then we're going to draw the other chair. So the flipped one, if you started with your two parallel lines going this way, now they're going the opposite way. So if they were going down from left to right, now they're going up from left to right. Again, don't worry too much about how pretty this is at this point. It should just look something like this. And now that methyl group is equatorial up, and the hydrogen is axial and down. So in a chair flip, up and down, do not change, but axial and equatorial do. So up stays up and down stays down, but the axial, the straight up and down, becomes the equatorial, the diagonal up and down. And that happens for every single position on that ring. So if you do that flip, you should see every one of those hydrogens moving from either axial to equatorial or equatorial to axial. Now, much like when we looked at the ethane or butane conformations, we can talk about these as being more or less stable. Anybody have an idea of which one of these would be more or less stable and why? One of these conformations is more stable than the other. Which one do you think it is? The first is why? It's more. So lost my pen. Oh, here. So you're saying this one is more away from the stuff than this one is? More staggered? Okay. Any other arguments, other ideas? Thinking. I'm going to actually replace that with a fully built methyl group here so we can see this. So I'm going to take another black thing and I'm going to put 4 sticks on there with hydrogens on it. Oops, except for that one, which has this thing broken off a bit. Did you get the idea? So when something large like a methyl group is in the axial position, it's a little bit less stable. And the reason is that it can interfere with the other things at axial positions. So you see that methyl group there in the axial position? It gets pretty close to these other hydrogens that are also in the axial positions. You see that? This thing getting close to these guys? And if these were any bigger than hydrogen, then they'd really get in each other's way. So when this flips to equatorial, you'll notice now this is way out of the way. It's not close to anything anymore. So this one is more stable. Large groups are more stable in equatorial position because it gets them out. So your reasoning was totally right with that you want to get the bigger groups out of the way of the other stuff.
I wasn't looking at the big group, I was looking at the hydrogen.
Oh, okay. So yeah, so looking at the bigger group, yeah. But your reasoning is correct, that you want to get this stuff away from the other stuff. And the best way to do that is to get it pointing outward of the ring, because when we bring it up into the ring, or bring it up to the axial position, it can more interfere with that stuff. So the last part of this then is how to convert from a flat structure or a regular line structure to a chair conformation, and make sure that everything stays in the right place. So let's say I want to look at something like this. Actually, let's make this an ethyl, so we can separate them a little bit. This is a fine line structure. Hold on, this is getting a little too tricky. Let me take off one of these. Okay, this is a fine line structure. The problem is when we go to put that into our chair conformation, it doesn't give us any information about which thing should go on which position, up or down or whatever. So we need to use some of the other type of drawing that we worked on a couple weeks ago to specify what exactly we're talking about. When we get into the next chapter after the exam, talk about stereochemistry, this will become really important. So I'm just arbitrarily going to change these to the wedges. Remember what the wedges mean? What? Yeah, so that means that those things are kind of coming out at you. And that means that there are dashes with hydrogens on them that were not shown. Now we have all the information we need to put this in a chair conformation using this little code. So in the chair, wedge is going to be up, dash is going to be down. All right. And if you get really good at this and you can move these things around in your head and all this stuff, then you can forget about this and you can do it however you want. But for now, to make it easier, to make it always right, we're going to remember that the wedge means up and the dash means down. So once you got that, then you just draw any chair conformation you want. Doesn't matter which one. I'll draw, most people have a favorite one that they draw a little bit better than the other one. That's certainly true for me. So I'm going to start with that, with this way. If you draw the other way better, you could start with that. I'm going to start with this one. So now we have to figure out where to put those things. So what I'm going to do is go back to the line structure and number the carbons in the ring. Numbering carbons is always a good idea. We've already talked about that with respect to naming, but keeping track of all your stuff is really important, and this is a good way to do that. So if we were to name this, we would start here and go 1, 2, 3, 4, 5, 6. So I'm going to do the same thing. Now, it does not matter where you start numbering on your chair conformation, but it does matter that you go in the same order. So this is counterclockwise. So I'm going to stick with counterclockwise in my chair conformation. Where do you want to start? Okay, kind of the same place, so like here? Yeah, all right, sounds good. So we'll go 1, 2, 3, 4, 5, 6. We've got substituents on 1 and 2, so that's where we're going to focus. That's where the stuff's coming off here. So on carbon number 1, we have an ethyl and a hydrogen, and the ethyl's on the wedge and the hydrogen is on the dash. So the first thing you should do is draw in both bonds, because we learned how to do that. We've got axial going down. Oops, stick with colors here. Axial going down and equatorial going out. And I mean, I know I did that quickly, but once you get practice with all this stuff, you'll be all right too. A lot of people, when they get started, like to just draw the chair conformations with all the bonds on every carbon. Just right away, you just draw it with all the bonds there, because that's how you practice doing it. That's fine too. And then they erase what they don't need later, or they just put in hydrogens later. That's fine. However you get those lines there at the right angles is great. And we're going to do the same thing on number 2, which has axial up and equatorial down, like that, kind of squiggly down. All right, now we're set up. So for carbon number 1, where do you think the ethyl group goes? Is it going to go on the equatorial or on the axial? Up. So which one's up? Right. The equatorial one on carbon number 1 is pointing up. The axial is pointing down. So you see that? So when we said this is up and this is down, it doesn't matter which is equatorial, which one's axial. Up is up, down is down. So on carbon number 1, we have to put that ethyl group right here. And that means the hydrogen goes here. So this one's up, this one's down. If we had started on another carbon, if we had made this carbon number 1, then that ethyl group would be axial, and that's fine. As long as it's up, that's what's important. That's why we put both bonds in first, so we can find the one that's up and find the one that's down, and put the things on them accordingly.
So let's just say for the number 1 on the hexane, if we made hydrogen up and the other one down, then it would be switched here.
That's right. Yep. So then how would you fill in number 2, the next carbon over? Okay, so the axial is going up on this one, so what should we put up there? Right. So that's going to get the CH3, and this is going to get the hydrogen.
Okay, so you said the
Right.
drawings, but if we had to plot it, it would look different.
It would. So let's try that, and let me see if I can convince you that that's actually the same. So what if we picked this one, which is the other chair conformation? And where do you want to start this time? Same place? Okay. So 1, 2. So we draw in the bonds for carbon number 1. Axial, equatorial, axial, equatorial. So then on carbon number 1, the ethyl group still goes up, but now that up is axial, and the hydrogen is equatorial. And over here, the up is equatorial, and the down is axial. So you're right, that looks pretty different from what we did before. But that's just because it's the other chair conformation. So it is the chair flip. If we build that, let's say I'll just use I'll keep my methyl group, but I'll use a red ball for the ethyl group. Okay, there's the first one that we drew. And then if we flip it, we actually have the second one. With the, whoops, that's the same one. Yeah, with the ethyl group going up and the methyl group out to the equatorial side. So as long as you follow the rules that you're numbering in the same order and wedges up and dashes down, you're always going to get it right no matter how you draw your chair. You might have one or the other chair conformation, but you're always going to have a correct one. The tricky part becomes, how do you flip it? Or how do you make sure that you're still drawing the same thing when it is flipped? All right, so let's do some practice here. Now that we've got some ideas on how to draw these things. Firstly, we can use names to help us with this too. If we have substituents that are both on wedges or both on dashes like that, we call those cis. Cis being the same. So you already learned this from somewhere, apparently. From mine?
Yeah.
Okay. Did we do this? Did we not?
Both the alkanes, because alkanes are supposed to be alphabets.
Yeah.
YouTube for the alkanes.
It was probably from a different, it must have been from a different class
then.
then.
Trans.
Okay. I believe you. I think it was from a different class because we haven't done this yet here.
No, I missed.
Wait, why is the dash not the bottom part?
I just to show another example, or it doesn't matter where it is. If there's two of them anywhere on the ring, that's called cis because they're either both wedges or both dashes. If you have one of each, that's called trans.
It wasn't the rings. Your rings is kind of,
It was for the double bonds? Okay. Yeah, we definitely haven't gotten there yet. So that was from Chem 100 last year. We'll get to that tonight, hopefully. So if we go back up to this one, this is 1-ethyl-2-methyl cyclohexane, but that's actually not enough of a name because it doesn't tell us the orientation of those two. So we need to call this cis 1-ethyl-2-methyl cyclohexane, and that gives us the full name.
and the dash. So we make it triangle.
It's because, right, the things on the dashes here are the hydrogens. So those aren't in the name. The ethyl and the methyl are the ones are on the same, are on, right. So that's the cis.
One ethyl, two methyl, cyclohexane.
Right, right. Let me write that.
Color, dash, or just
Another dash. So this is cis, 1, ethyl.
get the dash.
No. No, I don't mark off for stuff like that. As long as it's clear that you're naming things correctly and, you know, using the rules, I think that's fine. The point of things like naming rules is communication. Are you describing a particular structure unambiguously, specifically? If so, great, then it's right. If there's something that is not clear, that's when it's a problem. That's kind of my philosophy of it. Okay, let's practice some of these things. Well, one thing I might ask, draw both chair conformations of trans 1, 3, I'm running out of room here. Trans 1,3 dimethyl cyclohexane. How do we do that? Yeah, first we would draw the flat structure. So that would be a cyclohexane with, and it doesn't matter where we start, but we can number like 1, 2, 3, 4, 5, 6. And then that means we'll draw a CH3 on 1 and 3. And one has to be on a wedge and one has to be on a dash. And that's called trans. Because they're on opposite sides of the ring. Like one is in front of the ring and one is in back of the ring. Now when we get into that stereochemistry, we'll have to be more specific than that. Because there's actually, it's a little bit more complicated, but for now, we just say that this is trans. There's actually 2 different possible trans ones, but we'll get into that later. Either one would be okay at this point. So we've got a flat structure. What's the next step?
Draw a chair.
Draw a chair. So everybody draw a chair, whatever your favorite chair is. And see if you can draw this structure in that chair. I'm not going to do it first for you. You try it first. And then we'll look at it. Okay, let's get these chairs up on the board. We won't put them on the computer where the whole internet can see them. We'll just put them on the board. And you can even use this cool orange marker. Right. Let's get a few different ones. Take your time to get it set up. When you think you got something on your paper, let's see if we can see it. Yes. Thanks. You get another one? Thanks.
How do you know when to draw axes?
Good question. A couple ways I've used to remember that. So one is that. Okay. So if you see the two bonds kind of going upward, like that, like this is two. The two that are leading up to that point are going up. So that means the axis is going up.
Okay.
These two are going down for an arrow. So that's pointing to the axis. That's one way that people remember it. The other way is to just remember one of them. Like the right edge of this piece of chair always goes up. And you can always go up, down,
No. So it's basically.
that just, yeah. No, that just tells you that it's straight up or down. So if you know one of them, you can get all the other ones. It's like if there's one position that you're always really clear on, you can count ultimately around.
So then what does it have to do with?
It doesn't. It just tells you where it's going to go. So you don't have to care about it. You have to draw the lines in the right angles, but then you ignore that and you look for sister trans about the depth. So like at this position, this axial will be up and equatorial will be down. So if you need to make something up, you go there, if you need to put something down, you go there. But at this position, it's the opposite. Axial is down, equatorial is up.
Is that right?
That's what this is. This is up. This is down. That's just a rule that we wrote down. Great, thanks. How about one more? Please.
No.
I like the color coding too.
Oh, yeah.
I have to keep them separate, otherwise it's all gonna.
Well, we will talk about it. You put it up on the board first. Well, it's okay.
I'm so challenged. All right, I put on my other ones or something.
Yeah. Is this really intentional group? Okay. No one's gonna think. We're not gonna think badly of each other for putting some bad chair confirmations on the board. Anybody else want to add to the display? All right. So let's think about these. What do you think about them? Again, we're not being judgmental. This is the first day, and I have to say all of these are really good, especially considering the first day. Even if this were not the first day, I would say these are all really good. They may have some small things that we might correct. None of them are wildly off base or anything like that. So really nice job. If you're looking at these based on what we've seen, can you think of any things that don't quite seem to work on any of these? Yeah. Is what? Mm-hmm. Something looks a little funky.
The
Or choose
axials
it.
or the axial.
Here,
Yeah.
right? Yeah. So, oh, I didn't realize there was a brown one too.
Oh, I have it on two instead.
Yeah.
Okay, so yeah, so this one, they are at 1, 2 instead of 1, 3. The other issue here is even if this had been 1, 2, at this position, the axial should be up like that, and then this one should come down like that. So there wouldn't be one over there. But we know it's not there anyway, so we'll just fix this.
So they don't, so the axial and the equatorial don't have to be parallel to like any part of the chair structure itself.
The equatorial does, the axial does not. The axial just goes straight up. Okay, now is this right? Right, methyl group should go down. So that means that should be the hydrogen. Now what do you think? Okay? Okay. Would you make any other corrections about these other ones? Now notice, well, I guess before that, this one also, I think looks good, but notice that a different 1 and 3 were chosen here. So you went 1 and then 3, and this one is 1 here and then 3 there. That's fine. Those are both correct. There's nothing wrong about that. These are both the same structure. They're just kind of rotated a little bit, is what it would be in real life. So, so those are fine. What about this one? Seems okay? Yeah, it looks good. One thing I would recommend with this one, if you could just like rotate it a little bit this way. It's really fine, but it's right on the borderline. And the reason for that is that if you're really being parallel here, you're almost not going to be pointing down on the equatorial, and that's going to start getting into that gray area. So if you could just kind of rotate the whole, do you do it with the parallel lines first? Yeah, so just make your parallel lines a little bit flatter to start, and everything else should be great. But notice on this one, because she started at even a different carbon from everybody else, the methyl group ended up axial up here and equatorial down over there. Again, still fine. As long as it's up at 1 and down at 3, that's fine. Doesn't matter where you start. It doesn't matter which one's axial or equatorial. It's the up or down pattern. These are all good. Okay, so nice job. So now, once you have decided on a chair and once you've drawn one down, so either any of these 3 or however you did it, now you have to draw the other chair conformation, and now your options are not quite as open. So I'm gonna actually, since this is the biggest one, I'm gonna use this one to demonstrate how we do that. I'm gonna redraw it on here. this one went like this, right? H, CH3, like that. I didn't quite leave myself enough space, so it goes over the line a little bit. That's fine. Now we need to draw what happens when this thing flips. So first thing we do with that is we draw the other chair. Now that you all have a favorite, looks like two of you like this one and one of you likes the other one. Now you got to draw both of them. You got to get the other one in there too. So we're just going to draw the other chair first. And now we no longer have that freedom of just starting wherever we want and just numbering it however we want, because we're a little bit limited by where we started with. So we're going back to the first one and numbering it. 1, 2, 3, 4, 5, 6. And now we have to think about which carbon maps where on the other chair. That is, when one of these carbons flips down or flips up, what does it become? So are any of them clear to you? Is it clear which carbon goes to which other carbon?
It'll be in the same spot.
Right, it'll be pretty much in the same spot. So you see the one on the end here, number 2? That's still going to be the one on the end over here, number 2. The one that's kind of on the right in the bottom portion is going to be on the right in the bottom portion, and so forth. You see that? That mapping? They look a little different because they're in a little bit different angle, but relative to each other, what?
It's going like this.
Right, right. So once you get a couple down, then you can just finish the numbering on the ring. What a lot of people like to do is start at the ends, because the leftmost end and the rightmost end are usually pretty clear in both chairs. Like, it's clear to know which one is on the far end of each side. No. Once you do a bunch of them, you'll get used to where they will or won't interfere with stuff, but that doesn't matter. All right, so now we need to make sure that now that our numbers have mapped correctly, we want to keep our substituents in the same place, up-down wise, and on the same carbons. So we draw in those lines, again, the axial, the equatorial on number 1, the axial, the equatorial on number 3. And now on number 1, the CH3 is up, it stays up. On number 3, the CH3 is down and stays down. I should have extended that a little bit lower so it was clearer. And the other ones are the hydrogens. And now we have a correctly drawn chair flip. So the key with the chair flip is do not switch up, down. On the chair flip. So CH3 on number 1, it was up in the flat structure. It's up in chair number 1, and it's up in chair number 2. This is a common source of confusion because we have this whole axial equatorial switching business. Don't worry about that. Up has to stay up, down has to stay down. If that's the case, you'll be fine. All right, let's try another one. Yeah.
Really? It's not really about the company itself, but I feel like maybe one day I don't know about everybody else. Is there a way you could like almost like an exam review where it's kind of like work, so we can bring it in on Monday so we can check? Like almost like homework where I'd bring it in and you could check and make sure we're doing the exam next Wednesday.
Yeah, let's do something like that. That's a good idea.
I mean, the problems in the book are one thing, but they're not the same as the problems you get. Some of them are like
Right.
really simple, and so like maybe if like even if you gave us numbers out of the book that kind of show what we like have the way we've been taught.
Yeah. So a really good one in this book. And because it's not going to get any harder than this, is 3.38. And if you have an older version of the book, it's this question that has A through D of these 4 different chair forms, or these 4 different cyclohexanes. And it says draw both chair forms of each and indicate which one is more stable in each one.
So 3.38.
3.38, it's on page 101. All right, and we'll plan on going through those 4 on Monday during lab. Somehow we'll fit it in while we're waiting for something. All right. So that said, let's do another practice problem with our last 10 minutes here.
Skateboards.
A skateboard sign?
Yeah. Colored yellow and black.
That'd be a pretty nerdy punk skateboard sign.
Or
I like it. Yeah.
Or go. You want to start a skating game?
I do. That'd be fun.
With words of dog.
Yeah.
Words of Oregon.
There you go. I'm in. I feel like, I don't know, I haven't gotten my skateboard out in a few years. I feel like I'd hurt myself if I tried it again.
Especially if you made her skateboards just like that.
Yeah.
So now for the numbering here, would you really?
All right, so I guess, yeah, you distracted me. I didn't finish the instructions here. So the instructions here are draw both chair conformations. In this case with naming, we would start with the bromine and call that bromo, but for the purposes of this, because we haven't really talked about that yet, just number it however you want. Just keep your numbering consistent in the chair conformations so that you can do it right. But so the question here is draw both chair conformations of that molecule.
But in any other situation, you don't.
Right. Draw the 2 chair conformations for this one. Like what we did, but now with this one. So now we have there's a third substituent here, as you can see. That also means that we can't use cis and trans. Cis and trans only applies to 2 things. So if we needed to name this, we need some more rules that we haven't gotten to yet. You don't need to always draw the hydrogens. Sometimes some people find it useful so that you don't put something on the wrong bond if you have them both there. But no, you don't need to draw the hydrogen.
I don't understand this like at all with any of it. I feel like every time we talk about it, my brain just goes like project information, and
Okay.
I don't know why. Because like when I look at this, I don't even know where to begin.
Well, the good news is you got two nice chair confirmations there that look fine. They look really good. So now it's how do you put those in? How do you attach these? So you've got a number. That's good too. You got that
But I
number.
don't even know how you're supposed to decide how to number it.
It's up to you.
You can number it however you want.
You can number it however you want. So this one went, you started with 1 here, but you could start anywhere with 1
Yeah.
and then just go around the same way.
Okay.
The way you did it is fine. So then you say there is a CH3 coming off of number 1. So there's going to be a CH3 coming off of number 1.
And it's supposed to be down,
And
right?
it's supposed to be
Which is-
down. So what I would do is draw the 2 possible positions on number 1, which is axial down and equatorial up.
And how do you know that?
That comes from practice, from doing this over and over again, so that you know where these things are supposed
So
to
it
go.
always
on
looks
each one.
exactly the same?
Right. Yep.
Why do you need to do that if you know that this is down?
You don't. If you know that that's down, great. Then it's axial down, and then you're done.
But what
But
if
like
we have
number
one that's
2,
up on 1?
then it would be on the up, which is equatorial, this way. That's when you would move the angle. The heavy strong like this.
Okay. So since this is down, we just go down.
Yep.
This H3. And then this one is also down on 2.
Right.
So then it's going this way, right?
Yep. Okay.
And then this one is up on 3. Which means it's going down like this.
Yep, I got it. That's perfect. I would move it a little bit this way so that it's parallel with this one and this one. Oh, I guess it is parallel with this one.
Okay.
Those two are supposed to be parallel. Yeah,
Okay.
that's great. That's fine.
So you lied. They're not that good.
What?
The pictures.
They're
if
fine.
they were good.
They're fine. I'm just being specific because we're just starting on this. But if that were your answer on an exam, it would be fine.
So the number, yes. So when you're flipping, the numbers shift down if you're going clockwise, and shift up if you're going counterclockwise. Like here, does that make sense?
No.
Okay, so there,
doesn't in your head, it's
well, I just,
Okay.
if you answer this yes, then I know that it's working. Okay, so we started here,
Yeah.
1, 2, 3. So then when I flipped it,
Yes.
1, 2, 3. So it shows counterclockwise here it's 1, 2, 3. Which is, these make more sense.
Yes, your numbering is correct.
Yeah, that's why I was
You
double
do the
checking.
wrong,
Yep.
It's just. Say like numbers and.
Like, so I numbered them. So,
That's
one, and I did the chair, the one in the orange. I started with a 1 on the part of the and then when I flipped it, it dropped down to that bottom. And then we do, oh, I mean, so we have 1.
But it doesn't. You have to draw it like that move.
Yeah, like, because.
Oh.
To, like, here. Drop in a sense.
it goes that fast.
Straight. The up and down is-
We're just trying to figure out a way to all the numbers. Sounds like.
So, that's right. This one went down. Right. This is the problem with throwing the
There's like a lot of things in the chapter.
You're tempted to always use straight lines.
I can put it on chapter.
Well, yeah, no.
Yeah, and I'll look it up online and then I'll look at the answer. They're teaching it, they're further ahead.
I don't know. Okay, I don't know.
I would really
I struggle.
That's
That's
why
something
I
that's big.
Okay, so it's
Okay.
really up and down.
Yeah.
It's up and down.
Yeah.
It's linear.
Well, no. That's the problem. Because you can either be linearly up and down, that's called axial. Or you can be angularly up and down, we call that square.
Okay, so
Look at
when
your model.
I see the dash, I know that's
Right.
it's linear. Is that incorrect?
That's incorrect. That just means,
That's how you-
okay, so imagine
I mean,
there's a straight line, so imagine there's a point.
Start redoing them again, still be you every time.
Anything that's on that wedge would be out this way.
Right.
So that includes both the things that are straight like this and the things that are angularly that way. So depending where it is in the ring, up is always up, but it's either be straight up or angularly up, just depending on where you put it.
Okay, right, here's Joe. Right, that's right. Maybe that got longer.
That is, angles and everything are great with that. In your drawing, everything was very nice. There's one mistake. You numbered these clockwise. You numbered these, or you numbered these clockwise and then these counterclockwise. You ended up having in the wrong spot. But otherwise, everything was good.
So then I would here. So then I would.
So roaming should be, if you want to start with one there, then this should be CH3 there and CH3 there.
Okay, so how do I know?
You put them, that's why I think it'd be helpful to just draw all the substituents in, all the lines that are possible. And then we can say, I want to put it on this carbon. Let's say it comes up with it goes on this carbon. Up is up, so it goes there. If it were down, it would just go down. So that carbon, where's it? Yeah, so if you can
So
draw
it's always
that,
gonna mirror this.
right, or the other one. Yeah. So you can say, all right, let's say this is our number one. Number one turns out to be, okay,
Number one is number.
Yeah.
going to guess. So you're going to stick
I
your
know
hand
the same.
because that's the down. for that carbon. So number two is here, that's down two, right? Or here. Yeah, you're right. So that's also down, right? So that goes that one because that's down.
That's what physiology.
So sometimes I can say.
And that will actually switch. as they're
A lot
shifting.
easier.
So,
That's
I
almost
like one thing in Andy.
All right, we have to actually go. So I'm trying to get around to everybody's work.
It's right.
Okay, then pull up.
It's so much easier.
I guess not.
I can't get mine off.
It's that, they're going to lose drawing.
Yeah, that's all. Except you forgot to agree.
Wait.
Oh, there we go. That one.
But yeah, that's wrong.
There's getting.
Be careful when you do that.
Yeah,
So did you go in that after you did these?
I was.
Okay. Because these start, when you start to get these close to the vertical,
Yeah.
that gets a little messed up. But these will look good.
These are, well, that's what I was trying to, I was gonna say, I was like, it's still have like this shit on that.
Yeah.
So I was like, this is the best way to do it. So good.
Really good. You'll see a lot of extra parallels like that as you look it up. But some people,
Yeah.
If you show it that way, they'll go, that makes it more confusing.
I don't
That's
think
great.
so.
So,
Okay, and then,
that's, yes.
You like shapes? Well, no, I do. Yeah, it's gonna be easy for you to do.
I'm just gonna discuss, so like,